Let's wrap up section 4.1, the formal definition of the derivative. Last time we learned that the derivative of a function f at x equals a is defined to be f prime of a, which equals the limit as h approaches 0 of f of that value a plus h minus f of a all over h. And just to emphasize this, we would do this process and we would get a number, like 5 or -2 or something like that. Now, instead, we're going to treat the derivative as a function, and this will help us out in a couple of ways, right? It'll allow us to find the derivative at multiple points very quickly, but it'll also allow us to see what the derivative does, how the derivative behaves as a function. Let's look at an example, right? If f of x equals square root of x plus 3, then find f prime of x. Well, f prime of x is going to be defined to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So all we're doing is replacing an a with an x. But that means that our answer is not going to be a number. It's going to be another function. Right? So let's write this out. F prime of x is going to equal the limit as h approaches 0 of the square root of x plus h plus 3 minus the square root of x plus 3 all over h, right? Do you see how I'm getting this from this and that from that? So if we continue this, well, first of all, we're going to get 0 over 0. What do you think we do? We multiply by our best friend, the conjugate. You don't need the parentheses there. I'm just doing them for illustrative purposes. That's a plus sign, by the way. All over, and then itself. And we get, of course, the limit as h approaches 0. Remember, the top is going to get cleaned up. The bottom is going to be messy, but we don't really worry about that. X plus h plus 3 minus x plus 3 on the top, right, because both the radicals go away. And on the bottom, we get h times all this mess. Right, and you might notice that a couple of things cancel here. I'll just use black, right? This cancels, that cancels, and we're left with just an h. And then you might notice, oh, wait a minute, something else cancels. H, those cancel, and we just have a 1 on top, right? So just to be clear, we have the limit as h approaches 0 of 1 over all this junk. I'm going to get rid of those parentheses there, right? We didn't need them. And you might notice we don't even have an h anymore. And so we just write, okay, I guess our answer is 1 over, and then this is just going to be 2 root x plus 3. Right? So note that our answer is f prime of x equals this function. Right? That expression. Right? Our answer is a function. Okay? So f prime is the derivative of f. Just in general, we don't need to specify at a point. Okay? Taking the derivative of f is called differentiation. And if we differentiate y equals f of x, then we write dy over dx equals f prime of x. The reason we get dy over dx is because, just as a little aside, the limit is as delta x approaches 0 of let's call this delta y over delta x is equal to, it's just another way of writing the derivative. Just another way of writing the derivative, right? It comes from y2 minus y1 over x2 minus x1 being the slope, right? Anyway, here's another example, right? Given y equals blah, find dy over dx. So here's dy over dx, which is going to equal the limit as h approaches 0 of all of this, guys. We're going to have to write 4x plus h plus 2 squared minus 4x plus 2 squared all over h. Now, this is a little bit of a doozy. There's going to be a little bit of simplification here, all right? A little bit of algebra we have to do. So I guess for starter, yeah, let's just FOIL this whole thing, right? So we're going to FOIL this, and we get 16x plus h quantity squared, right? Because we square this first term, right? That's the f in FOIL. Plus 16x plus h, that's the OI part of foiling, right? 2 times 4x plus h, and then, right, that's the outer and the inner, and then plus 4. So this turned into this. That is going to turn into this minus 16x squared plus 16x plus 4. And then this all will be over h. Okay, and then we're just going to simplify even a bit more. And we're going to get 16, right? I'm just going to FOIL the x plus h, which is going to be x squared plus 2xh plus h squared. So it's going to be 16x squared plus 32xh plus 16h squared. Let me move this down a little bit. There. Okay. All right, by the way, this is all that. And this is, well, that's the first part of the yellow stuff. Plus 16x plus 16h plus 4. And that's all our yellow highlighted stuff. Right, and then this is just going to be, I'm just going to distribute the minus I, minus 16x squared minus 16x minus 4. All right, so we have that. And of course, it's all divided by, all divided by h. All right, and if you notice, we can cancel some stuff. The way this is always going to work out is that all of the non-h terms should cancel, because the goal of this is always, always, always to divide out the top by h, to divide out the bottom by h, right? That's always the goal of all this. So I'm going to factor out an h, and I'm going to get 32x plus 16h plus 16h, oh no, sorry, plus 16. Yeah, I guess that's what I get. And all this is times an h, right? Notice I factored out this h, right? That's the h that I factored out. Okay. And then on the bottom, we're also going to have an h, and well, that's kind of nice. We just cancel it out. And so our answer is going to be 32x plus 16 times 0 plus 16, which is just 32x plus 16. And that's our answer. Okay. Again, it's a function. It's not a number. It's a function. Now, here's the nice thing about differentiating the function and not just, and like just in general, not a number. We can then plug in any value we want after differentiating, instead of doing that whole limit process with the number and then having to do that whole limit process with another number if we want the derivative at another point. So call this guy f of x, and we have f prime of x is going to equal the limit as h approaches 0 of 9 minus the quantity x plus h. Make sure that x plus h is in the parentheses, right? The h is getting subtracted too. And then minus the square root of 9 minus x, and then this is all over h. We know we're going to get 0 over 0, so we multiply by the conjugate over the conjugate. And then we have limit as h approaches 0, and we know this is going to get cleaned up a bit. This will be 9 minus x plus h minus 9 minus x, right? The radicals go away. The bottom is a mess that we will not even try to simplify. And of course, some stuff will cancel. The 9 minus 9. The minus x minus, just want to point this out. This is really minus x minus h. Do we see that? So really the minus x cancels with the plus x, right? Minus negative x is plus x, right? So just to be clear, we have on the bottom the limit as h approaches 0 of negative h all over h times, again, this lovely mess, try that again. Okay. And at this point, we can cancel out the negative h. Remember, it's -1 on the top. Just be a little careful about that. And then we're just going to take the limit, right? And it winds up being -1 over 2 root 9 minus x, right? Because we plug in 0 for h. And we just get the square root of 9 minus x plus the square root of 9 minus x. It just reduces to that. But now, that's not what I asked. I asked at the value x equals 0. So now we can say f prime of 0 equals -1 over 2 root 9 minus 0. And we can reduce that to being -1 over 2 times 3, which is -1/6. And they say, oh, shoot, no, sorry, I actually wanted you to find f prime of 5. Okay, well, we can do that too. F prime of 5 is going to be -1 over 2 root 9 minus 5, or -1 over 2 times 2, which equals -1/4. Right? So you see how this drastically reduced our workload if we needed to find the derivative at multiple points. And in addition, we can't see this quite yet, but in general, we will notice a pattern about these derivatives, right? We know how it behaves. That's not the most intuitive function, but we can plug in any value of x and know how the rate of change of f at that point begins. All right, now, lastly, just want to point out that when we're differentiating a function, we're using the limit techniques that we already know, right? And right now, that means we can take limits with indeterminate forms, 0 over 0, right? That's the one thing we get for polynomials, 0 over 0 for square roots, and then infinity minus infinity for fractions, right? And we have techniques for all three of those, right? So if you're good with your limit techniques, then you're good with taking the limit definition of the derivative. Now, I just want to spend a couple of minutes on a slightly different topic, but it's still important, a more geometric approach to this whole thing. We say a function f is differentiable at x equals a if f prime of a exists. If f is differentiable at x equals c, for all c in an open interval, then f is differentiable on the open interval from a to b. So I guess that begs the question, how can a function not be differentiable at a point? And well, the answer is, well, if f prime of a, which equals the limit as h approaches 0 of f of a plus h, yes, we're going back to the point definition of the derivative at a point, does not exist. Well, when does that happen? Well, it happens when the left side doesn't equal the right-hand side. So, of course, if the function is discontinuous, right, in any sort of way, right, if we have a discontinuity here, there, we have a jump discontinuity maybe, we also have slightly more subtle issues, something called a cusp. We could also have, this is kind of weird, but like a vertical tangent line. We also could have, let's try that. Could have a vertical tangent line. We also could have a corner like that. Those are all non-differentiable, right? So here is a problem, here is a problem, here, there's a problem. I guess I'll call this like R, and this is S, right? Those are all problematic shapes of a graph if this is y equals f of x, right? And the reason is because the tangent line, is either not unique or vertical, right? For example, there is no tangent line to a point if the point doesn't exist, right? So, like, these guys don't even have tangent lines, right? So forget about those. But something like here, this tangent line is going this way, like from the left, but the tangent line from the right is going that way, so it's not a unique tangent line at that point. Here we have a vertical tangent line. Here we also have a vertical tangent line. And here, again, we have a vertical tangent line this way from the right and that way from the left. So the tangent lines just are not unique. All right, here are some functions that are not differentiable, right? Any discontinuous function, that's 1. Also like, 1 over x, for example. You also could have y equals x to the 2/3, which is 1 over the cube root, oh, sorry, sorry, that is the cube root of x squared. You also could have y equals the absolute value of x. That gives the corner. Okay. So here's another question. Is the differentiable function at a point also continuous at that point? And the answer is yes. Function has to be continuous in order to be differentiable. So if it's differentiable, then it's got to be continuous. And that's all.